You are not sitting still. It feels like you are. The room around you holds its shape. The objects on the table do not slide. The light from your lamp does not tilt. If you reached for a glass of water right now, you could do it without thinking, because the laws of physics in your room behave the way they always have, and nothing about this evening seems unusual. But this is a story about how that stillness is an illusion, a very deep one. And the moment you understand the actual scale of the motion you are inside of, the floor under your chair begins to feel like something else entirely. The Earth is spinning. About once every 24 hours, it carries you around its axis at a speed close to 1,000 miles per hour at the equator. You do not feel it, because everything around you is spinning at the same rate. You only see the consequence. The sun appears to rise. The sun appears to set. The sky moves. The Earth is also orbiting the sun. About 67,000 miles per hour. Over the course of a single year, it carries you in a long, slow circle around our star, a journey of nearly 600 million miles, completed quietly while you are doing the things you do. The sun is not still either. The sun is orbiting the center of the Milky Way galaxy, about 490,000 miles per hour. It takes the sun roughly 225 million years to complete a single orbit around the galactic core. Our star has only made this trip about 20 times since it was first ignited, and the Milky Way itself, the entire galaxy, every star you have ever seen with your naked eye, every constellation our species has ever named, every nebula, in every photograph, in every book of astronomy, is moving. It is moving fast. It is moving in a specific direction. And nobody in the entire history of human science has been able to fully explain what it is moving toward. There is something out there. Something with the gravitational mass equivalent of tens of thousands of galaxies, possibly more. It is hidden behind the dust of our own galactic plane, in a part of the sky we have never been able to see clearly. It is invisible, it is enormous, and it is pulling our galaxy, our entire neighborhood of 100,000 galaxies, toward itself, at a speed that has been measured carefully, repeatedly, by independent teams across decades, and which no model of the universe was prepared for. Tonight, we are going to walk slowly into that pull, not as a headline, not as breaking news, as a story about a question that the universe has been quietly asking us ever since we first learned how to listen. You are inside the motion. So am I. So is the planet beneath this room. So is every star in the sky tonight. We are all falling toward the same place, and we do not yet know its name. If the idea of an entire galaxy moving and not knowing exactly what it is moving toward is the kind of thought you want to rest with, please, take your time. Settle in. Let your shoulders soften. Let the room around you go quiet. Tonight is long. Tonight is slow. Tonight is for sitting with the parts of the cosmos that turn out to be much closer to home than they first appear. Now we begin. Part 1. The stillness that was never stillness. To understand why this story matters, you first have to abandon a very old picture of the cosmos. For most of human history, when our species looked up at the night sky, what we saw was a kind of frozen architecture. The stars seemed fixed. The constellations seemed permanent. The same patterns that the ancient navigators of Polynesia steered by, the same stars that the early astronomers of Babylon catalogued, the same lights that have hung above every human shoulder for tens of thousands of years, appeared night after night in the same places. This stillness is one of the great illusions of our cosmic vantage point. It exists because the distances are so vast that even the fastest motions in the universe, when viewed from far enough away, appear to be still. A star moving across the galaxy at hundreds of thousands of miles per hour, seen from another star many light years away, will appear to drift across the sky over the course of thousands or millions of years, far too slowly for any single human lifetime to notice. But the stillness was always an artifact of distance and time, not a feature of the universe. The first hint that nothing in the cosmos is actually still came in the early 20th century. In 1929, Edwin Hubble, working at the Mount Wilson Observatory in California, announced a result that quietly reshaped every assumption astronomers had ever made about the cosmos. He had measured the distances to a number of nearby galaxies, and he had measured the wavelengths of the light arriving from them. And he had noticed something specific. The light from almost every galaxy in his sample was redshifted. Redshift, in plain language, is what happens to a wave of light when its source is moving away from you. The wave gets stretched. Visible light, when stretched, moves toward the red end of the spectrum. The greater the redshift, the faster the source is receding. What Hubble found was not just that some galaxies were redshifted and some were not. It was that the redshift increased in proportion to the distance. The farther away a galaxy was, the faster it was moving away from us. This was a pattern, a universal pattern. And the only natural explanation was that the universe itself was expanding. The space between galaxies was growing. Every galaxy, in every direction, was being carried away from every other galaxy by the slow swelling of the cosmos itself. This discovery, which is the foundation of modern cosmology, took a still universe and replaced it with a moving one. But the picture Hubble drew, the picture that became the standard model of expansion, was a picture of motion in only one sense. It described the average flow, the Hubble flow, the motion that all galaxies share simply by virtue of being inside an expanding space. What Hubble's law did not describe was something quieter, something that lived underneath the average, something that astronomers would not begin to understand for several decades after. When you measure the velocity of a galaxy, the total motion you record is made up of two parts. One part is the Hubble flow, the recession driven by cosmic expansion. The other part is the galaxy's individual peculiar velocity, its own private motion through space, caused by the gravitational pull of whatever happens to be near it, its own way of falling. For the cosmos at large, those two motions are usually combined into a single redshift number. Most analyses are about the average. The Hubble flow is so dominant at large distances that the peculiar velocities of individual galaxies become small corrections, easy to overlook. But once astronomers learned to look for them, the peculiar velocities began to tell a different story. They began to map the gravity of the universe. Where galaxies were falling towards something heavier than themselves, their motions revealed the heavier thing, even when the heavier thing could not be seen. This is the beginning of how we learned that we, ourselves, were falling. Our galaxy's own peculiar velocity, the part of its motion that is not just the Hubble flow, was estimated for the first time using a different kind of evidence entirely. Not redshift, not direct observation of nearby galaxies, something subtler. In 1964, two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to clean up a persistent radio noise in a horn antenna they were using for satellite communication. They had cleared the antenna of pigeons. They had checked the wiring. They had pointed the antenna in every direction they could think of. And the noise remained. A faint, even hiss coming from every part of the sky, equally, regardless of where they pointed. It turned out the noise was the cosmic microwave background. The leftover heat from the Big Bang itself, redshifted now, after 13 billion years of cosmic expansion, into the microwave part of the spectrum. The discovery was eventually awarded the Nobel Prize. It was the moment when the Big Bang stopped being a theory and started being something we could detect directly. But once astronomers had measured this background carefully enough, they began to notice that it was not perfectly even after all. There was a faint pattern in it, a pattern called the dipole. On one side of the sky, the cosmic microwave background looked very slightly hotter. On the opposite side, very slightly cooler. The interpretation was simple. We were moving. The Earth, and everything it sits on, was traveling through the cosmic microwave background in a particular direction. As we moved, the radiation in front of us was slightly compressed and appeared slightly hotter. The radiation behind us was slightly stretched and appeared slightly cooler. The pattern in the dipole was the signature of our own motion, written into the oldest light in the universe. When astronomers worked out the speed implied by the dipole, they got a number. Roughly 600 kilometers per second, 370 miles per second, over 1 million miles per hour. That was how fast the local group of galaxies, the small cluster of galaxies that includes our Milky Way, our neighbor Andromeda, and a few dozen smaller galactic companions, was moving relative to the cosmic microwave background. It was, in some sense, an absolute speedometer reading. The cosmic microwave background is the closest thing the universe has to a universal reference frame. Measured against it, our local group was moving fast, faster than the Earth orbits the Sun by a factor of more than 15. And the direction was specific, toward a region of sky in the southern celestial hemisphere, in the direction of the constellations Centaurus and Hydra. A region that, when astronomers looked at it carefully, contained almost nothing visible to explain the motion. Something out there, in a direction that crossed almost exactly behind the dust of our own galaxy, was pulling fast, pulling everything. And we, sitting on a small planet, on a small star, on a small spiral arm of the Milky Way, were going along for the ride. Not by choice, not by design, simply because gravity had decided, long before our species existed, that the Milky Way was going to spend the rest of its life falling. The question was, falling toward what? Part 2. The 7 astronomers who refused to let it go. In the early 1980s, a group of 7 astronomers, working across multiple institutions, began to take the question of our peculiar motion seriously enough to try to map its source. They became known, informally, as the 7 Samurai. The name was a kind of inside joke. Their formal collaboration had no official title, only a long string of last names appearing together on a series of papers that over the course of several years would slowly build a picture of cosmic motion that nobody had previously imagined was there. The names were Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner. Astronomers, all of them, with very different backgrounds, working at very different institutions, brought together by a shared suspicion that the dipole in the cosmic microwave background was not the whole story. Their suspicion was specific. If our local group of galaxies was being pulled in a particular direction, that pull had to be coming from somewhere. There had to be a mass concentration somewhere out there in the direction the cosmic microwave background dipole was pointing. That was responsible for the motion. The cosmic microwave background told us we were moving. The seven samurai wanted to find what we were moving toward. The technique they used was elegant in concept and brutal in practice. The idea was this: if you know the distance to a galaxy from one method, and you know its velocity from another method, then any disagreement between those two numbers is telling you something. The galaxy's true distance, measured by some property that does not depend on its motion, gives you a baseline. The galaxy's redshift, which would normally translate cleanly into distance under simple Hubble expansion, gives you a different number. Subtract one from the other, and what remains is the galaxy's peculiar velocity, its private fall. To measure distances independent of redshift, the seven samurai used a property of elliptical galaxies that had been discovered only a few years earlier. It was called the Faber-Jackson relation, after Sandra Faber, one of the seven, and Robert Jackson, who had described it in 1976. The relation links the size and brightness of an elliptical galaxy to a quantity called its velocity dispersion, which is, in essence, a measurement of how fast the stars inside it are moving in random directions. Because elliptical galaxies of the same intrinsic size and brightness will produce the same velocity dispersion regardless of how far away they are, the relation gives you a way to measure how big a galaxy actually is, independent of its distance. And once you know how big it actually is, you can compare that to how big it appears, and from that comparison work out, with reasonable precision, how far away it must be. The seven samurai applied this method to a sample of about 400 elliptical galaxies scattered across the local universe. What they found, slowly, paper by paper, between 1986 and 1987, was a coherent flow. It was not just our local group that was moving. It was thousands of galaxies across hundreds of millions of light-years of space, all flowing in roughly the same direction. The motion was systematic. It was not random. It was not the chaotic small-scale dance of galaxies wandering through their local neighborhoods. It was a current, a river of galaxies, a vast, gentle, continuous flow, moving toward a particular region of the southern sky. The region of sky toward which the flow was pointing already had a known feature. There was a galaxy cluster there called the Norma cluster, sitting in the direction of the constellations Centaurus and Norma. The Norma cluster was substantial, but on its own, it was nowhere near massive enough to explain the flow that the seven samurai were measuring. The flow was being driven by something larger, something behind the visible cluster. Something that, when you tried to add up its mass from the velocity field of the galaxies falling toward it, came out to roughly the equivalent of tens of thousands of typical galaxies, concentrated into a volume far larger than any cluster previously catalogued. In the papers, the seven samurai gave it a placeholder name. They called it the Great Attractor. The name was meant to be temporary, a working label until the underlying mass concentration could be properly identified, mapped, and explained. The expectation was that, with better instruments and more careful observations, the Great Attractor would resolve into a familiar kind of object, a particularly massive galaxy cluster, maybe a small chain of clusters, something that once we got a clearer view of it, would look like the kinds of structures we already knew how to describe. That expectation was about to run into a very serious problem. The Great Attractor was located almost exactly behind the disk of our own galaxy. If you had been able to draw a straight line from Earth in the direction the cosmic microwave background dipole was pointing, the line would have passed straight through the densest part of the Milky Way, the galactic plane, the thick, dust-filled, gas-filled, star-filled disk that we live inside, which, when seen from the inside, is bright and crowded, and when used as a window to look outward through, is opaque. Astronomers had a name for this region of the sky. They called it the zone of avoidance. The zone of avoidance is not a metaphor. It is a real physical region, a band stretching across roughly 10 to 20 degrees of the sky on either side of the galactic plane, where the dust and gas of the Milky Way absorb almost all visible light coming from anything behind it. Galaxies in the zone of avoidance are extremely difficult to see in optical wavelengths, the wavelengths most ground-based and space-based optical telescopes are designed for. The zone of avoidance covers, depending on how generously you define it, somewhere between 15 and 20% of the entire sky. It is, for traditional astronomy, a wall, and the Great Attractor was on the other side of that wall. When the seven samurai had pointed at the direction of the flow, they had pointed almost exactly at the zone of avoidance. The thing pulling our entire local universe was, by an unfortunate cosmic coincidence, sitting in the one part of the sky that we could not directly look at. For some astronomers in the late 1980s and early 1990s, this was reason for skepticism. There was a school of thought that the Great Attractor might not exist at all, that the apparent flow the seven samurai had measured was an artifact, a statistical mirage, the result of selection effects or systematic errors in the distance measurements, or the unfortunate fact that you cannot easily verify a mass concentration that you cannot directly see. The skepticism was reasonable. Extraordinary claims in science require extraordinary evidence. A massive structure, hidden behind the galactic plane, dominating the motion of 100,000 galaxies in our local universe, was an extraordinary claim. The evidence so far was indirect. The next decade was spent making the evidence less indirect. Astronomers learned to peer through the zone of avoidance. The trick was to use wavelengths of light that are less affected by dust. Visible light gets absorbed and scattered. Infrared light passes through more easily. Radio waves and X-rays pass through almost unhindered. By building infrared, radio, and X-ray surveys aimed specifically at the zone of avoidance, astronomers could begin to see, faintly, the galaxies that lived behind the dust. In the 1990s and into the early 2000s, several major surveys, including the 2-micron all-sky survey, called 2MASS for short, and dedicated radio surveys carried out by the Parkes Telescope in Australia and the South African Telescope at Hartbeespoort, began to systematically map the previously hidden parts of the sky. What they found behind the galactic plane was not nothing. What they found was a wall of structure. The Norma cluster, already known, was confirmed to be embedded in a much larger network of galaxy groups and clusters. Behind it, mapped piece by piece as more sensitive instruments came online, was an enormous concentration of galaxies that, when summed up, did not quite add up to the gravitational pull the seven samurai had originally measured. There were galaxies there, there was mass there, but not enough. The Great Attractor, when its visible matter was finally mapped, was substantial but insufficient. It explained part of the flow. Not all of it, and astronomers were forced to ask a question that had been quietly building in the background for years. If the Great Attractor was real, but not large enough on its own to fully account for the motion we were measuring, what else was out there? The answer, when they began to follow the flow further outward, turned out to be even larger than the Great Attractor itself. The flow did not stop at the Great Attractor. The galaxies of our local universe were not falling only toward the Norma cluster region. They were falling further, past the Great Attractor, past the zone of avoidance, towards something much more distant, much more massive, something that, when astronomers in the 1990s and 2000s began to characterize it, turned out to be the densest concentration of galaxies in the local universe. Its name had been given decades earlier by an astronomer who had no idea, when he first noticed it, that it was at the bottom of a gravitational sink that included our own galaxy. His name was Harlow Shapley. The thing he had seen, sitting in the southern sky, in the direction of the constellation Centaurus, was, eventually, named after him, the Shapley concentration. And we, on Earth, in the Milky Way, in the local group, somewhere on the outer reaches of a vast supercluster, are still falling toward it. Right now, as you breathe in, as you breathe out. The whole architecture of our cosmic neighborhood is in motion, and the gravity of the Shapley concentration is the slow, distant note underneath that motion. The horizon, the destination, the thing the river is running toward. What the Seven Samurai had begun, by chasing a strange dipole in the cosmic microwave background, was the discovery of an architecture that dwarfed every previous estimate of the size of structures in the local universe. The Great Attractor was not the answer. The Great Attractor was the foreground. The real question, lurking behind it, was what the Shapley concentration actually was, and whether it, in turn, was the bottom of the basin, or whether it was just one more step in a flow that did not, at any scale, ever quite settle. That question would be answered in part by a single word in a Hawaiian language, a word that astronomers borrowed in 2014, when they finally drew the boundary around the structure that contained us. The word was Laniakea. It means, in Hawaiian, immeasurable heaven. And it would turn out that even immeasurable heaven was not, by itself, enough. Part 3. The naming of an unnamed place. For most of the history of astronomy, our species had been content with relatively modest cosmic addresses. We knew that we lived on a planet. We knew that the planet orbited a star. We knew that the star was one of many stars in a galaxy. And we eventually learned, with increasing confidence over the 20th century, that our galaxy was one of many galaxies in a small cluster called the local group, which contained about 50 or so galaxies. And the local group, we knew, was sitting somewhere in the outer regions of a larger structure called the Virgo supercluster. The Virgo supercluster was, for most of the 20th century, the largest cosmic neighborhood we believed we belonged to. It was named for the Virgo cluster, the dense concentration of galaxies near its gravitational center, about 54 million light-years from Earth. The supercluster, all told, was estimated to span about 110 million light-years and contain about 100 groups and clusters of galaxies. It was, by any measure, an enormous structure. We were one tiny galaxy in a small group on the outskirts of a much larger gathering. This was the picture of our cosmic address that astronomy textbooks carried for decades. In 2014, an astronomer named Brent Tully at the University of Hawaii, working with Hélène Courtois, Yehuda Hoffman, and Daniel Pomerade, published a paper in the journal Nature that quietly redrew the map. What Tully and his collaborators had done was something that, in retrospect, sounds simple, but which had not been done before at the scale they did it. They had built a tool called Cosmic Flows. It was a catalog of galaxy distances and galaxy velocities, painstakingly assembled over years of careful observation from many different surveys using many different distance measurement techniques. Most galaxy maps, before Cosmic Flows, were maps of position, where the galaxies were. The galaxies were drawn as dots in three-dimensional space, scattered across the volume of the local universe. Cosmic Flows was a map of motion, where the galaxies were going. Each galaxy was not just a dot. It had an arrow attached to it, the direction the galaxy was moving, the speed at which it was moving. The arrow was the peculiar velocity, the private fall. When you draw enough of these arrows across enough of the local universe, you do not just see a static map. You see a flow field. You see currents. You see basins. You see places where galaxies are streaming inward and places where galaxies are streaming outward. You see the gravity of the universe, written in the motion of its inhabitants, even when the gravity itself is invisible. Tully and his team used the Cosmic Flows catalog to do something specific. They used a watershed analysis, the same kind of analysis a cartographer uses when mapping which streams flow into which rivers flow into which oceans cover which continental basins. Every drop of water on a continent belongs to some watershed. Every river follows the gravity of its terrain. By tracing the flow of water, you can identify the boundary that separates one basin from another. The watershed boundary is not always a visible feature on the surface. It is defined by where water goes, not by what you can see. What Tully and his colleagues did was apply that same logic at the scale of the cosmos. They followed the velocities of galaxies. They identified the boundary at which the velocity field changed direction. On one side of the boundary, galaxies were flowing inward toward a particular gravitational basin. On the other side, galaxies were flowing toward a different basin. The boundary itself was the cosmic watershed. When they drew the boundary that contained our local universe, the boundary that separated our flow from the flow of our neighbors, the result surprised even them. The structure they had outlined was about 500 million light-years across. It contained roughly 100,000 galaxies. The total mass within it was estimated at about 100 million billion times the mass of our Sun, in stars, gas, and dark matter combined. The Virgo supercluster, the structure that astronomy textbooks had been calling our home for decades, was not, on closer inspection, an independent supercluster at all. It was a small lobe, a subsidiary part of something much larger. The whole Virgo supercluster, when measured by velocity field, was just one corner of a vastly larger gravitational basin. That basin had not been named before, because it had not been seen as a coherent object before. The instruments to identify it as a single structure, the catalogue of velocities, the watershed analysis, had not existed at sufficient scale until Tully's team built them. They needed a name. The team chose Laniakea. The word is Hawaiian. It means immeasurable heaven. They picked it deliberately, both as a tribute to the Polynesian navigators who had crossed the Pacific Ocean by reading the sky, and as an acknowledgement of what the structure represented. A heaven of galaxies, larger than any previously mapped, the limits of which had only just become measurable. When Laniakea was first announced, the public response was, predictably, focused on the dramatic statistic. Our cosmic address had just gotten a new line. We did not just live in the Milky Way. We did not just live in the local group. We did not just live in the outer Virgo supercluster. We lived in Laniakea. We had a continent now, in the cosmic ocean, that we belonged to. A name for our place that took into account the actual geography of cosmic motion. But the most important detail in the Tully paper was not the size of Laniakea. It was the direction of its flow. Inside Laniakea, the entire structure, all 500 million light-years of it, was not gravitationally still. The galaxies in Laniakea were not just sitting in their basin, evenly distributed and quietly orbiting. They were flowing. The whole supercluster, on its largest scales, was in motion. The motion had a direction. It was flowing toward the Centaurus region, toward the place the Seven Samurai had been pointing at, decades earlier, when they first identified the Great Attractor. Laniakea, in other words, was the basin. The Great Attractor was the bottom of the basin, the point toward which everything in our supercluster, the whole 100,000 galaxies of immeasurable heaven, was draining. But that was not the end of the story. It was, in fact, the next chapter. When astronomers extended the velocity field measurements outward beyond Laniakea, looking at the flows of structures even further away, they found something that the Great Attractor alone could not explain. The flow did not stop at the Great Attractor. The Great Attractor itself was being pulled. The Norma cluster, the region behind the zone of avoidance, the entire bottom of our basin, was, in turn, falling towards something further out. That something was the Shapley concentration. The Shapley concentration sits, by current best measurements, about 650 million light-years from Earth, in the same general direction as the Great Attractor, just substantially further away. It contains an estimated mass equivalent to roughly 10,000 million billion times the mass of our Sun. It is the densest single concentration of galaxies in the local universe. It contains dozens of clusters of galaxies, all packed into a region of space that astronomers describe as the closest thing the nearby cosmos has to a gravitational megacity. The Great Attractor in this picture is not the destination. It is the foreground. It is what we see first, because it is closer, and because its mass is large enough to dominate the motion of the galaxies near us. But behind it, and pulling on it, sits the Shapley concentration, drawing not just our local group, not just our supercluster, but the Great Attractor itself, into a flow that runs across nearly 1 billion light-years of space. We are, in some sense, in a river that we did not realize was a river. The current we are riding is real. The destination is even further out than the first object we noticed. The whole architecture is in motion, and the part of the architecture closest to us is itself in motion, falling toward the part of the architecture beyond it. This picture, when you sit with it, has a certain quality. It has a kind of nested quality. We are inside the local group. The local group is inside the Virgo supercluster lobe. That lobe is inside Laniakea. Laniakea is flowing toward the Great Attractor region. The Great Attractor region is flowing toward the Shapley concentration. And the Shapley concentration, for all its enormous mass, is itself embedded in the larger network of the cosmic web, with filaments and walls and voids on still larger scales beyond it. There is no scale at which the falling stops. This is, in a literal sense, what cosmologists call cosmic flow. It is the rearrangement of matter, on every scale, under the influence of gravity. The smaller structures fall into the larger ones. The larger ones fall into the largest ones. The largest ones move slowly, over billions of years, into the densest concentrations. If you could speed up time and watch the local universe over 1 billion years, you would not see a static collection of galaxies hanging in space. You would see a slow, vast gravitational flow. Galaxies streaming along filaments, clusters tumbling toward each other, whole superclusters drifting toward larger concentrations, falling, gathering, accumulating. We are part of that flow. We are not observers of it from the outside. We are inside it, drifting with it, carried by it, the way a leaf is carried by a slow river. What the Seven Samurai had identified in the 1980s was not just a structure, it was the direction of our drift. What Tully and his colleagues had identified in 2014 was not just a name, it was the boundary of the river we were inside of. The boundary, as they drew it, ran for 500 million light-years. The flow inside the boundary moved at 600 kilometers per second. The destination, as far as we could trace it, was the Shapley concentration, 650 million light-years away. That was, for a while, the picture. Then, in the years after Laniakea was named, even Laniakea began to look small. Part 4. A quiet hour with what we are falling through. Before we go further, let us slow down for a moment. What we have just walked through is, when you stop to picture it, almost incomprehensible. So let us not rush. Let us take the picture and let it settle. Imagine, if you can, that you are looking at the local universe from somewhere far above it. You are not in any galaxy. You are floating in some imaginary vantage point above the entire structure. Below you, spread out across hundreds of millions of light-years, is a vast, intricate, three-dimensional pattern of light. The pattern is the cosmic web, the bright clusters of galaxies, the threads of filaments running between them, the dark voids in the spaces between the threads. You can see Laniakea from your imaginary vantage point. It looks like a vast, irregular shape, traced out by the bright clusters at its edges and the filaments running through it. Inside Laniakea, the small, faint shape of the local group sits near one outer rim. Inside the local group, the Milky Way is a single point of light, indistinguishable at this scale from any other galaxy. Inside the Milky Way, the Sun is a single star among hundreds of billions, invisible. Inside the Sun's gravity well, Earth is too small to see it all. Now, in your imagination, set the scene in motion. You see, at first, very little change. At the scale we have been talking about, motion takes time. A galaxy moving at 600 kilometers per second is not moving fast on a cosmic scale. It is moving fast on a human scale, but the distances are so vast that even at that speed, the galaxy hardly seems to budge. So speed up time. Speed it up until each second of your imagined viewing represents 1,000,000 years of cosmic history. Now you can see the flow. The galaxies at the outer edges of Laniakea drift inward. The local group itself, with our Milky Way inside it, drifts gently toward the Centaurus direction, slowly, steadily, never stopping. The Virgo cluster, near the center of the supercluster lobe, holds its position roughly, but the flow around it is unmistakable. Streams of galaxies move in along the filaments. The whole structure is breathing inward, very slowly, on the scales of cosmic time. Speed up time again. Speed it up to where each second represents 1,000,000,000 years. Now, Laniakea itself is in motion. The whole supercluster, all 500 million light-years of it, drifts as a unit, toward the Great Attractor region, toward the Centaurus and Norma direction, toward, ultimately, the Shapley concentration, 650 million light-years away. This is the actual cosmic motion you are inside of, right now, tonight, as you sit in your room. The Earth is moving with the Sun. The Sun is moving with the Milky Way. The Milky Way is moving with the local group. The local group is moving with Laniakea. And Laniakea is moving toward Shapley. Every level of motion is real. Every level is happening simultaneously. The motion you do not feel is the result of being inside the moving thing. From the inside, the river looks still. From outside, the river is unmistakably flowing. There is something almost humbling about that picture. The stillness of your room is the stillness of the inside of a moving universe. Nothing is at rest. Nothing has ever been at rest. The cosmos has been in motion since the first instance after the Big Bang, and the pattern of that motion has been gathering galaxies into structures, and structures into superstructures, and superstructures into flows toward concentrations for nearly 14 billion years. You, sitting wherever you are sitting, are riding inside the latest moment of that motion. Your blood is moving in your body. Your body is moving on a planet. The planet is moving around a star. The star is moving around a galaxy. The galaxy is moving towards something that may be moving towards something else. And at no scale, in no direction, in no measurement we have yet made, is anything actually still. This is the deeper meaning of the Great Attractor. The Great Attractor is not just a faraway object. The Great Attractor is the destination of the river you are inside of. It is the gravitational reason that the Milky Way is heading where it is heading. It is the reason that the cosmic microwave background appears slightly hotter on one side of the sky and slightly cooler on the other. It is the reason that the constellations, when measured carefully enough, are not quite as fixed in their relative positions as they appear. The whole pattern of the local cosmos has been, and is, oriented toward this region. And in the slow, patient way of cosmology, we have only really started to understand what that means in the past few decades. Most of human history was lived in the assumption that the heavens were still. The Earth turns. We learned that. The Earth orbits the Sun. We learned that. The Sun orbits the galaxy. We learned that. But the galaxy itself, drifting towards something further still, was a relatively recent discovery, and we do not yet have a clean account of exactly what is at the bottom of the well. That part of the story, in some ways, is still being written. Let us return to it. Take a slow breath. Let your eyes settle. The river is flowing. We are inside it. There is nothing for you to do about that, and nothing that needs to be done. You have been falling towards Centaurus your entire life, and so has every person you love, and so has every star you can see, and the falling does not, on a human timescale, hurt anyone. It is simply what we are. We are part of the flow. The flow is part of the cosmos. The cosmos is, at its largest scales, in motion. That is what the data say. Part 5. The numbers that would not quite behave. There is a particular kind of unease that runs through cosmology now, an unease that has been growing slowly for the past 2 decades, and which the story of the Great Attractor sits uncomfortably close to. The unease is about velocities. When astronomers measure the speed at which the universe is expanding, the number they get depends on how they measure it. There are, broadly speaking, 2 main ways to measure the expansion rate, which is called the Hubble constant. One way involves looking at the very early universe, the cosmic microwave background, the patterns it shows, and calculating, from those patterns and the standard cosmological model, what the expansion rate must currently be. That method, as refined by the Planck satellite over years of careful observation, gives a value of about 67.36 kilometers per second per megaparsec. The other method involves looking at the local universe. You measure the distances to nearby galaxies using methods that do not depend on the cosmological model. You measure their recession velocities. You compare the two, and you read off the expansion rate directly. That method, as refined by Adam Rees and his collaborators over more than a decade, gives a value of about 73.17 kilometers per second per megaparsec. The two methods do not agree. They are both very precise. They both have small error bars. The disagreement between them, expressed in the language of statistics, runs at 5 to 6 standard deviations. In any other field of physics, that level of disagreement would be considered a crisis. In cosmology, where the measurements are extraordinarily difficult, the field had hoped for years that the disagreement would dissolve once measurement errors were better understood. That hope was directly tested when the James Webb Space Telescope, with its superior sensitivity and resolution, observed the same kinds of stars used in the local distance measurements. The hope was that James Webb would reveal a hidden systematic error, would shift the local value toward the cosmic microwave background prediction, and the tension would resolve. That is not what happened. James Webb confirmed the local measurements with high precision. The Hubble constant, measured from the local distance ladder using James Webb's improved data, came out at about 72.6 kilometers per second per megaparsec, almost exactly what Hubble had been giving us. Instrumental error, as a possible explanation for the disagreement, had been effectively ruled out. What remained, after the careful James Webb recalibration, was the real possibility that the universe is not behaving the way the standard model says it should. The discrepancy looked like a feature of reality, not a measurement artifact. Cosmologists began to use a phrase they had been reluctant to use: severe tension, the standard model under stress. Now here is where the story curves back toward the Great Attractor, in a way that most popular accounts do not quite emphasize. The local measurements of the Hubble constant are, by their nature, measurements made from inside our cosmic neighborhood. They are calibrated against galaxies in the relatively nearby universe. And the relatively nearby universe, as we have just seen, is not a typical cosmic neighborhood. It is a neighborhood that sits inside an unusually large void called the KBC void, named for Keenan, Barger, and Cowie, the three astronomers who first identified it in 2013. The KBC void is roughly 2 billion light-years across. Inside it, the density of galaxies is about half of the density measured on average across the universe. Our local group, our Laniakea supercluster, our entire cosmic neighborhood out to about 1 billion light-years from Earth, sits inside this lower-than-average density region. This is not a small detail. A region of lower-than-average density experiences different gravitational dynamics than the cosmic mean. Galaxies inside a void tend to be pulled toward its walls. As the void expands and empties over time, this expansion imprints an additional outward velocity component on the galaxies within it. If our location inside the KBC void introduces a systematic boost to the measured velocities of nearby galaxies, then the local expansion rate measurements might come out higher than the true global rate. Not because any measurement is wrong in a simple sense, but because what is being measured locally, from inside a void, is genuinely different from what is being calculated from the early universe. We would be measuring the universe from inside a bubble. And the bubble might be teaching us, in a quiet and consistent way, the wrong number. Whether the KBC void fully accounts for the Hubble tension is still contested in the literature. Some analyses suggest the underdensity is not pronounced enough to fully explain the entire discrepancy. Others find that once the void's influence is properly modeled, the tension shrinks substantially. There is no consensus. What there is, after years of careful measurement, is a clear acknowledgement that our position in the cosmos is not a neutral fact. It is a physical circumstance. It has measurable consequences for what our instruments tell us about the fundamental constants of cosmology. Now look at the picture. We are inside an unusually large void. The void is 2 billion light-years across. We are inside a supercluster called Laniakea. The supercluster is 500 million light-years across. The supercluster is flowing toward the Great Attractor. The Great Attractor is itself flowing toward the Shapley concentration. The Shapley concentration sits about 650 million light-years away. Beyond the Shapley concentration, the cosmic web continues, filament after filament, void after void, on scales we are still learning to measure. Our entire local cosmic geography is unusual. We sit in a low-density region. We sit inside a flow toward a higher density concentration. The architecture is asymmetric in detail, and the asymmetry shows up in our measurements of the universe's most fundamental quantities. This is not a comfortable place to find oneself scientifically. The standard cosmological model assumes that the universe, on large enough scales, is essentially homogeneous. It is supposed to look the same in every direction. The cosmological principle, the foundational assumption from which most of modern cosmology is built, says that there are no special places, no preferred directions, no anomalous neighborhoods. The local observations, when you take them seriously, raise a question. What if there are? What if, at the scale we live at, the cosmos is not as smooth as we assumed? What if the flows we are riding inside, the basin we are draining toward, the void we are sitting in the middle of, the Great Attractor pulling on our supercluster, the Shapley concentration pulling on the Great Attractor, are all part of a structure that is, at the largest scales, more complicated than the standard model has room to describe. Nobody is saying yet that the cosmological principle is broken. The careful work of refining the standard model continues. The hope is that, with better data, the apparent local anomalies will resolve into modest corrections within the existing framework. But the hope is not certainty, and the data is, in a quiet way, putting more pressure on the framework with every survey that comes online. The Great Attractor, in this sense, is more than a scientific curiosity. It is part of an evolving picture in which the local universe seems determined to be a little more interesting, a little less average, a little more in motion than the comfortable map said it would be. That picture is still being drawn. We are still inside the drawing. The river is still flowing, and the destination, when you press on it carefully, has more layers than the first naming suggested. Part 6. The thing that is also pushing for decades after the Great Attractor was first identified, the picture of our local cosmic motion was treated as a simple problem of attraction. There was a mass somewhere, and our galaxy was being pulled toward it. The puzzle was finding the mass. The story was a story of pulling. In the early 2000s, that picture began quietly to acquire a second character. Yehuda Hoffman, an astronomer at the Hebrew University of Jerusalem, had been working with Brent Tully and Helene Courtois, the same cosmic flows team that had identified Laniakea, on a deeper question. The original cosmic flows analysis had identified the basin we were inside of by following the directions galaxies were heading toward. Hoffman and his collaborators began to ask a different question. What about the directions galaxies were heading away from? In a flow field, motion is always relative. Galaxies are pulled toward concentrations of mass, but they can also appear to be pushed away from regions of unusually low mass. A void, surrounded by denser regions, will appear, when measured against the average flow, to repel the galaxies near it. Not because the void is exerting a force. Voids do not push. They have no mass to push with. But because the matter on the far side of the void, in the surrounding higher density regions, exerts more gravitational attraction than the empty interior of the void. The result, when you sit on a galaxy near the edge of a void, looks indistinguishable from being pushed. The galaxies on the side of the sky where the void lies appear to move outward, away from it. The galaxies on the side of the sky where the denser concentrations lie appear to be moving inward, toward them. The void, in effect, becomes a kind of repeller, a negative attractor. When Hoffman and his team applied this analysis to the cosmic flows data, they found something specific. Our local group, our Milky Way, our entire neighborhood was not just being pulled toward the Shapley concentration in the direction of Centaurus, it was also being pushed, almost exactly opposite to the direction of the Shapley concentration, on the other side of the sky, in the direction of the constellation Eridanus. There was a vast region of lower-than-average density. The galaxies in our area were being repelled from that region. The combined effect of pull from one direction and push from the opposite direction was producing the motion that the cosmic microwave background dipole had been measuring for half a century. The team gave the repelling region a name, the Dipole Repeller. In a paper published in 2017 in the journal Nature Astronomy, Hoffman, Pomerade, Tully, and Courtois described the discovery. The Dipole Repeller is a vast underdensity, a region of relative emptiness, sitting roughly opposite the Shapley concentration in the sky. Our local group is, in the language of their paper, being driven by the combined push of the Dipole Repeller and the pull of the Shapley Attractor. Each contributes about half of the velocity we measure relative to the cosmic microwave background. The two effects, working in concert, produce the motion we see. This is, when you slow down to think about it, a strange picture. Our entire cosmic neighborhood is in motion. The motion is partially driven by gravity from a distant mass concentration, the Shapley side, and partially driven by the absence of mass on the opposite side, the Dipole Repeller. We are being squeezed, in some sense, caught between an emptiness and a fullness, drifting from one toward the other, as gravity slowly drains us out of the empty side and pulls us toward the fuller side. The names in this story carry their own quiet weight: the Great Attractor, the Dipole Repeller, the Shapley concentration. They sound, when read out together, more like the cast of a myth than like the labeled regions of a scientific map. But they are the regions of a scientific map. They are real features of the local universe, identified through careful measurements of how galaxies are moving, and they describe a real architecture in which our position is not at a center, not at a boundary, but somewhere in the middle of a flow, carried by forces that are partly what is in front of us and partly what is missing behind us. There is a quality to this picture that I want to spend a little time with, because it does not come up often in the textbooks. When most people think about gravity, they think about it as a pulling force. A planet pulls a moon, a star pulls a planet, a galaxy pulls a star. Everything heavy in the cosmic landscape pulls everything light. What the Dipole Repeller reminds us of is that gravity, on the largest scales, is also a comparison. The motion of any particular galaxy is not just about the heaviest thing nearest to it. It is about the relative balance of mass on every side. When you sit between a heavy region and an empty region, the heavy region pulls more, the empty region pulls less, and the result is a motion away from the empty region and toward the heavy region. The motion does not feel different from a push, mathematically. It produces the same vector. It is just gravity, with mass on one side and the absence of mass on the other. The Dipole Repeller, in this sense, is not really pushing anything. The Shapley concentration is doing the pulling. The Dipole Repeller is simply the place where the pulling is not, and the absence of pulling, when you are caught between attraction on one side and lack of attraction on the other, looks indistinguishable from being pushed. This is a picture, when you sit with it long enough, that has a certain elegance. The cosmos is not pulling you toward the Shapley concentration only. The cosmos is also, on the opposite side of the sky, very gently, refusing to pull you back. You are caught in the asymmetry of the universe's own mass distribution. You are not being moved by something. You are being moved by the difference between what is on one side of you and what is not on the other. This is, in a literal sense, what cosmologists mean when they say that gravity, on cosmic scales, is sourced by everything, by every concentration of mass and every lack of mass. The motion of any object in the universe, including the entire Milky Way, is the integrated result of the gravitational influence of every other piece of matter, weighted by distance and direction. When you sit inside a flow, the flow is what every nearby massive thing is doing, all at once. We sit inside a particular flow. The Shapley concentration is the dominant attractor. The dipole repeller is the dominant lack of attraction. Together, they drive about 1,000 kilometers per second of bulk motion across our local supercluster. And we, on Earth, on the Sun, in the Milky Way, are inside that motion the entire time. Now, the dipole repeller raises a further set of questions, which the field is still actively working on. The first question is whether the picture really is this simple, whether the Shapley pull and the dipole repeller push really do account, between them, for the motion we measure. There are some indications, in more recent surveys, that there may be additional effects. Larger structures, sitting further out, contributing flows that have not yet been mapped. In 2023, Salman Khan and Daniel Pomerade, working with the same Cosmic Flows team, published a result identifying what they called a basin of attraction extending to roughly 500 million light-years across, encompassing Laniakea and significant portions of the surrounding cosmos. Their analysis suggested that the gravitational landscape we sit inside of is even more extensive than the original Laniakea boundary, that the cosmic flows we are riding may, in fact, extend further outward, with additional concentrations of mass, additional voids, additional features that the next generation of surveys will need to map carefully. The pattern of the cosmos, in other words, keeps revealing itself to be larger and more textured than each previous generation of surveys had assumed. We started with the local group. We expanded to the Virgo supercluster. We expanded further to Laniakea. Now we have a basin that may extend further still, and the limits of how big the structure we belong to actually is are still being measured. The second question is whether the dipole repeller is itself a real feature of the cosmic web, or whether it is, as some critics have suggested, partially the result of how we are reconstructing flows. Some analyses have raised technical objections. Others have proposed that the apparent push and pull asymmetry might be partly an artifact of the data reduction methods. The debate is, as of the most recent literature, ongoing. The majority view holds that the dipole repeller is a real and substantial underdensity, but the magnitude of its effect and the precise role it plays in our local motion are subjects of continuing analysis. The third question, the one that quietly hovers behind all of this, is whether there is anything at any scale that ultimately stops the falling. We are flowing toward the Shapley concentration. The Shapley concentration is, on its own scale, the densest concentration of galaxies in the local universe. But the Shapley concentration sits inside a larger cosmic web. There are other concentrations, on still larger scales, that may or may not be exerting gravitational influence on the entire region. There are great walls of galaxies stretching across substantial fractions of the observable universe. There are voids of comparable scale. Whether any one of these structures eventually serves as a final destination for the cosmic flow, or whether the flow simply continues, level after level, all the way out to the limits of what we can measure, is not currently settled. The fact that, even now, in 2026, with the most precise instruments humanity has ever built, we cannot draw a clean line at the bottom of the basin we are draining toward, is not a failure of the science. It is an indication of how big the architecture is and how slowly we are still mapping it. We have been pointed in this direction since long before our species existed. We will continue to be pointed in this direction long after our species is gone. The Earth, the Sun, the Milky Way, all of it, are riding a current that began billions of years before there was anything to ride it, and that will continue billions of years after there is anything to notice. We are passengers in a flow that is older than us, larger than us, slower than us, and more patient than any human story has been. The Shapley concentration, 650 million light-years from where you are right now, is, in this picture, where the river presently seems to be running. It is not, in any human timescale, somewhere we will ever reach. The Milky Way will never collide with it. The Milky Way will not, in fact, get appreciably closer to it within the lifetime of any species that will ever exist on Earth. The motion is real. The destination is real. But the timescales involved make the story a story of a tendency, more than a story of a journey. We are tending towards Centaurus. We have been tending towards Centaurus for a very long time. We will continue to tend towards Centaurus for as long as the universe lasts in any form recognizable as the universe we are currently inside of. That is, in some sense, the answer to the question. What are we falling toward? We are falling toward Shapley. We are falling away from Eridanus. We are caught in the slow asymmetry of how mass is distributed on cosmic scales, and we will be falling in this same direction for as long as the cosmos continues to exist in its current configuration. Part 7. The dark flow that may or may not be there. There is one more chapter to this story that has to be told carefully, because it sits at the edge of what current cosmology is willing to accept as established, and at the same time, if it is right, it is one of the most important findings in the field. It is called the dark flow. In 2008, Alexander Kashlinsky, an astrophysicist at NASA Goddard Space Flight Center in Maryland, working with collaborators including Fernando Atrio Barandella, Dale Kochevsky, and Harold Eberling, published a paper that, on its face, was about a fairly technical effect in cosmology called the kinematic Sunyaev-Zeldovich effect. The effect involves the way photons of the cosmic microwave background can be very slightly shifted in temperature when they pass through hot gas in galaxy clusters. If the cluster is moving toward you, the photons get a tiny boost in energy. If the cluster is moving away from you, the photons lose a tiny bit of energy. By measuring the cosmic microwave background carefully in the directions of large galaxy clusters, you can, in principle, measure the bulk motion of those clusters. What Kashlinsky's team did was apply this technique to a sample of about 700 clusters, distributed across a substantial fraction of the sky. They wanted to know if the clusters, on average, were moving in any preferred direction relative to the cosmic microwave background. What they found was unexpected. The clusters appeared to be moving coherently in roughly the same direction as our local group, toward the Centaurus and Hydra region. Toward the same general direction, the Great Attractor and the Shapley concentration had been pulling everything else. That, by itself, was not the surprise. Of course, nearby clusters, sharing the same cosmic neighborhood, would have correlated motions. They are gravitationally connected. They are part of the same flow we have been describing. The surprise was the distance scale. The clusters in Kashlinsky's sample were not just nearby. Some of them were 1 billion light-years from Earth, or more, and they appeared to be moving, on average, in the same direction. The flow seemed to extend much further out than the gravity of any known structures could explain. The Shapley concentration was massive, but at 1 billion light-years away from us, its gravitational influence on a distant cluster on our side of the universe should have been weak. The standard cosmological model predicted that the bulk motion at that distance should be small and approximately random. Coherent motion across 1 billion light-years was not in the prediction. Kashlinsky and his collaborators called the effect dark flow. The name was chosen deliberately, dark, because it could not be explained by any visible mass distribution within the observable universe. Flow, because it was a coherent bulk motion across a vast region of space. The paper was controversial from the moment it appeared. The signal was at the edge of detectability. The systematic uncertainties were significant. Other groups, using the same technique with different data, reported either smaller signals or no detection at all. Some analyses found the original measurement consistent with statistical fluctuations. The Planck collaboration, in subsequent more careful measurements, reported results that were difficult to reconcile with the original dark flow claim. The current scientific consensus, as of the most recent analyses, is that dark flow at the original strength claimed by Kashlinsky's team is not strongly supported by independent measurements. The effect, if it exists at all, is much smaller than originally reported. But the possibility has not been completely ruled out either. Some bulk flow on scales of a few 100 million to 1 billion light-years remains plausible. The exact magnitude is contested. The interpretation, if the effect is real, is frankly unsettling. Here is why. If there is genuinely a coherent flow extending beyond 1 billion light-years, and that flow cannot be explained by any structure inside the observable universe, the explanation has to come from somewhere outside the observable universe. The observable universe is the region of space within which light has had time to reach us since the Big Bang. It is not the entire universe. It is just the part of the universe close enough that signals from it could have arrived at our telescopes by now. The actual universe almost certainly extends well beyond what we can observe. How far beyond, we do not know. If structures outside the observable universe were pulling on matter inside the observable universe, we would not be able to see those structures directly. They would lie permanently beyond our cosmic horizon. But their gravitational influence, if strong enough, could in principle leave a detectable signal in the form of a coherent flow. This was, when it was first proposed, a startling idea. It suggested that the universe extending beyond our cosmic horizon was not simply more of the same, that there were features out there, mass concentrations or other structures, large enough to influence the motion of objects inside the observable universe. We would, if dark flow were real, be detecting the gravity of things we could never see, of regions we could never visit, of structures whose existence could only be inferred by their pull on the matter we have access to. This is one of the more philosophical implications of cosmology. The universe we can see is large. The universe we cannot see may be larger. If the dark flow interpretation is correct, the things we cannot see are not just out there in some abstract sense. They are influencing us. They are part of why we are moving the way we are moving. Whether or not dark flow turns out to be real at the originally claimed magnitude, the scientific landscape it points at is worth taking seriously. We measure motion. We model the masses we can see. The motion we measure does not always match what the visible masses can produce. Either there are masses we have not yet identified, or the masses we have identified are arranged differently than we have realized, or the gravitational effects we are calculating are incomplete. The cosmos has been telling us in subtle ways for years that the simple picture is not quite the right picture. The Great Attractor was the start of this story. Galaxies were flowing in a coherent direction. Something massive was pulling them. We could see hints of the something. We could not see the whole thing. The zone of avoidance kept the foreground hidden. The Shapley concentration, when it was finally mapped well, did much of the explanatory work. The dipole repeller filled in the picture from the other side. But there is, lurking in the data, a residual question. Whether even the Shapley plus dipole repeller picture is really the whole story of our cosmic motion, or whether there is some additional contribution sitting either inside our observable universe but not yet adequately mapped, or sitting outside it entirely. That residual question is, in a sense, the limit of what we currently know. We have mapped the basin we are inside of. We have mapped the foreground attractor and the foreground void on the opposite side. We have characterized, increasingly well, the cosmic web on every scale we can reach, and we have not yet been able, in any final way, to close the books on whether the picture is now complete. The honest answer is that the books are still open. The Cosmic Flows project has continued, with ever more data, ever more galaxies, ever more refined velocity measurements. The Euclid Space Telescope, launched by the European Space Agency in 2023, is now adding deep redshift surveys to the picture. The Vera Rubin Observatory, scheduled to begin operations in earnest in the late 2020s, will produce a fundamentally new map of the local universe. With each new data set, the architecture of our cosmic neighborhood becomes clearer, and the picture of what we are falling toward gains another layer of detail. What we already know, with high confidence, is the shape of the puzzle. We are moving. The motion is real. The motion has been measured many independent ways. The dipole in the cosmic microwave background was the first hint. The peculiar velocities of nearby galaxies were the second. The flow field measurements of cosmic flows are the third. Every method gives a consistent answer. We are heading toward the Centaurus and Norma direction, at roughly 600 kilometers per second relative to the cosmic microwave background. What is at the bottom of that flow is, in part, the Shapley concentration. What is on the opposite side is, in part, the dipole repeller. What may or may not also contribute, on still larger scales, is the question that the dark flow controversy has, in some sense, kept alive. We have not yet finished the map. The river is real. The destination, in detail, is still being measured. That is where cosmology, as of this evening, finds itself. Part 8. What it means to be inside the flow. Everything we have walked through tonight has ultimately been about a single fact. We are not still. The room around you is not still. The earth under your room is not still. The sun is not still. The Milky Way is not still. The local group is not still. Laniakea is not still. Even the structures pulling on Laniakea are themselves embedded in the slow flow of the cosmic web at every larger scale. There is no level in the architecture of the universe at which motion stops. There is no place where the gravitational rearrangement that has been going on for nearly 14 billion years pauses, and everything settles into a final configuration. This is, in some ways, a revelation about what the universe actually is. We tend to think of the cosmos as a thing, a vast collection of objects, distributed across space, hanging in their positions, occasionally interacting through gravity, but mostly just existing, fixed, observable, mappable. What we have been learning over the past century of careful observation is that the cosmos is not a thing. It is a process. It is gravity, slowly, patiently, sorting matter into ever more concentrated configurations. Galaxies into groups, groups into clusters, clusters into superclusters, superclusters into flows, flows into still larger basins, on still larger scales, all the way out to the limits of what we can measure. The Great Attractor is one of the local features of that process. The Shapley concentration is another. The Dipole Repeller is a third. Laniakea is the supercluster boundary that defines our gravitational neighborhood. The KBC void is the larger void our supercluster sits inside of. Every one of these is a feature of a single underlying process. The universe, on its largest scales, is in the act of becoming more clumpy, more concentrated, less smooth. The smooth, nearly uniform distribution that emerged from the Big Bang is, very gradually, being reorganized by gravity into the cosmic web we observe today. And that reorganization is still going on. If you could stand outside the universe and watch it for 1 billion years, what you would see is not a pretty picture of stars and galaxies. What you would see is a flow, a dance of matter on every scale, slowly draining into the deepest gravitational wells the cosmos contains. The Shapley concentration, in our local part of the cosmic web, is one such well. The galaxies of Laniakea are slowly, patiently, on timescales that will outlast every species that has ever or will ever exist on Earth, draining toward it. We are part of the draining. This is, I want to say carefully, not a dramatic situation in any human sense. We are not in danger. The Milky Way is not going to fall into the Shapley concentration in any human timescale. The motion of our galaxy toward Centaurus is something like 1 to 2,000 kilometers per second, and the distance to the Shapley concentration is 650 million light-years. The arithmetic does not produce a meeting in any cosmic timescale, even ignoring the expansion of space, which will, in fact, prevent the meeting from ever happening at all. Dark energy, the mysterious component that is accelerating the expansion of the universe, is gradually overcoming the gravitational pull of even the largest structures. In the very long run, the Shapley concentration and the Milky Way will move apart, not together, not because gravity has been switched off, but because the expansion of space is, on the largest scales and over the longest times, stronger than the gravity holding things together. So we are not falling into the Shapley concentration in any literal sense. We are tending toward it. We are pointed in its direction. The arrow of our motion has been pointed there for billions of years and will remain pointed there for billions more. But the destination is not, in fact, going to be reached. The river is flowing, but the river is also being carried apart from itself by the slow inflation of the space the river is flowing through. There is, when you sit with it, something almost beautiful about that picture. We are inside a flow. The flow is real. The direction is real. The destination is real. And yet the destination is also, in the fullness of cosmic time, slipping away from us. We are pointed towards something we will never quite reach, on a journey that will outlast every conceivable trace of human civilization. The cosmos, in its largest motions, is a kind of patient longing. Galaxies leaning toward a place they cannot ever fully arrive at, because the space between them is widening faster than their motion can close it. It is a picture that, when you slow down to feel it, has a certain quiet quality, the kind of quality that it is possible to find peace in. We are, in the end, just visitors here. The motion is much older than we are. The motion will continue much longer than we will. The mass concentrations that are pulling us are doing so without any awareness of our presence. The voids that are emptying near us are doing so without any awareness of our absence in them. The cosmos is in motion for its own reasons. It does not need us to notice. We notice anyway. This is what we do. As a species, we notice. We have built telescopes that can read the dipole of the oldest light in the universe, We have measured the velocities of thousands of galaxies. We have given names to the structures we did not even know existed a century ago. The Great Attractor, Laniakea, the Shapley concentration, the Dipole Repeller. We have mapped, slowly, the river we are inside of. And in mapping it, we have come to understand, in a way no civilization before us could understand, that we have always been in motion, that we have been moving towards Centaurus longer than there have been continents on Earth, that every star our ancestors looked up at, every constellation any human has ever drawn, every life that has ever been lived under our sky, has been part of the same flow. That is, when you turn it over, a kind of belonging. We are not isolated objects sitting in the void. We are part of a current. Every cell in your body is made of atoms that were forged inside stars that themselves are being carried by the same motion that is carrying you. The water you drink today is in motion toward the Centaurus direction. The breath in your lungs is moving with the planet, with the sun, with the galaxy. Nothing about you is separate from the cosmic flow. You are an arrangement of atoms inside an arrangement of stars, inside a galaxy, inside a flow, inside a basin, inside a network. And at every layer of that nesting, you are being carried, slowly, gently, along with everything else. That is what we are. That is what we have been, since the beginning. That is what we will continue to be, until our story, however it ends, ends. The Great Attractor is not just a curiosity in a textbook. It is the destination of the river you are inside of. It is one of the reasons you exist, where you exist. The geometry of mass in the local universe on which the Milky Way's whole long history has unfolded is the geometry that the Great Attractor and the Shapley concentration and the Dipole Repeller have between them helped to shape. Without that geometry, the Milky Way would not be where it is. The Sun would not be where it is. The Earth would not be where it is. You would not be where you are. The motion that produced your location, in this sense, has been working on the universe for far longer than your species has existed. You are sitting, right now, on the result of nearly 14 billion years of cosmic flow. You are, in a deep way, part of where the flow has gone so far. The next chapter, the chapter that comes after this evening, the chapter the next generation of telescopes will write, will refine the map further. We will learn more about what is at the bottom of the basin. We will learn whether the Dipole Repeller is the only push or whether there are other voids and other concentrations that contribute to the picture. We will learn, perhaps, whether dark flow has any residual reality. We will probably learn other things that, sitting here this evening, we cannot anticipate. But the basic shape of the answer is already clear. Something is pulling our galaxy. Something is also pushing it by being unusually empty on the opposite side of the sky. The pulling and the pushing combine to give us a motion of about 600 kilometers per second relative to the cosmic microwave background, in the direction of the constellation Centaurus. The Shapley concentration is, at present, the most plausible candidate for the dominant attractor. The Dipole Repeller is, at present, the most plausible candidate for the dominant repeller. Beyond these, the architecture of the cosmic web continues, and there may be additional contributions we have not yet fully mapped. We have been moving in this direction since long before the Earth existed. We will continue moving in this direction long after the Earth ceases to exist. The motion is patient. The motion is slow. The motion is, on human scales, undetectable. On cosmic scales, the motion is part of the slow rearrangement of matter that has been going on since the Big Bang and will continue for as long as gravity exists. And we, on this small planet, on this small star, on this small spiral arm, in this small corner of Laniakea, are inside it, have always been inside it, will continue to be inside it. This is our address. This is our drift. This is the river. Part 9. The long arc of not knowing. It is worth pausing here, near the end of this story, to say something honest about how science actually arrives at the picture we have just walked through. Most of the great cosmological discoveries are not single dramatic moments. They are slow accumulations. The Great Attractor was not announced one Tuesday afternoon by a scientist holding up a photograph. It emerged over years from quiet measurements made by careful astronomers, refined paper by paper, debated in the literature, contested in conferences, and slowly absorbed into the working picture of the field. The Seven Samurai's original measurements in the 1980s were preliminary. They were doubted by some specialists at the time. The first decade after the Great Attractor was named involved active debate about whether the flow was really there, or whether it was an artifact of the distance measurement method. The infrared and X-ray surveys of the zone of avoidance in the 1990s refined the picture. They confirmed that there was a real concentration of mass behind the galactic plane. They also revealed that the visible mass, when finally summed up, did not quite add up to the gravitational pull the Seven Samurai had inferred. That gap drove additional searches. The searches eventually revealed the Shapley concentration as the more distant, more massive, more dominant attractor. The Cosmic Flows project over the 2000s and 2010s transformed the field by providing the velocity data needed to draw the basin boundaries with confidence. Laniakea was named in 2014. The Dipole Repeller was identified in 2017. The dark flow controversy, which began in 2008, has been quietly working through the literature for nearly 2 decades. Different teams, using different methods, have reported different results. The most recent careful analyses suggest the original strong dark flow signal is not present at the magnitude originally claimed, but the broader question of whether bulk motion extends beyond the influence of identified structures is still, in some sense, an open one. The Hubble tension, which we touched on in Part 5, is itself an active crisis in cosmology, still developing as the data improves. It is, when you read it carefully, also part of the story of how our local cosmic position influences what we measure. What I want to highlight in this slow summary is that the picture we have built tonight is not a finished textbook. It is a working draft. It is the best current understanding, drawn from many independent lines of evidence by many independent teams over multiple decades. It will continue to be refined. This is, I think, an honest thing to acknowledge. Cosmology, like every science, makes its real progress through patient work and revision. The names we use today, the Great Attractor, Laniakea, the Shapley concentration, the Dipole Repeller, will continue to be useful. The numbers attached to them, the masses, the distances, the flow velocities, will continue to be sharpened. The picture, as a whole, will continue to be amended. We are not, at the end of this story, in a position to say definitively what we are falling toward, in the sense of having a final, complete, unrevised account. We are in a position to say that we are falling, that we know roughly which direction, that we know roughly how fast, and that the most plausible explanation involves a combination of a distant mass concentration, a nearby underdensity, and the slow accumulation of structure on cosmic scales over 14 billion years. That is honest. That is what the data say. The poetic version of the story, the version where we are mysteriously called toward an unseen attractor, is not entirely wrong. It captures something real about the experience of being inside the cosmos and discovering that we are in motion in ways we did not previously understand. But it is also, in its dramatic form, slightly more dramatic than the actual situation. The Great Attractor is not, in any literal sense, mysterious in the way that, say, dark matter is mysterious. We have a pretty good idea of what is there, even if the zone of avoidance keeps the foreground partially obscured. The Shapley concentration is not, in any literal sense, hidden in the way that, say, the interior of a black hole is hidden. We have mapped it with infrared surveys and other techniques, and we know its rough mass and its rough position. What is genuinely unsettled is the question of how all of these features fit together at the largest scales. Whether the local geography we have characterized is the whole story, or whether it is one chapter in a larger story we have not yet finished reading. That open question, more than any single dramatic finding, is the actual frontier. And the frontier, in cosmology, has a way of turning out to be more interesting than the headlines suggested. The map of the local universe in the year 1960 was a map that showed our local group inside the Virgo supercluster, and stopped there. The map in 2014 showed Laniakea and pointed at the Shapley concentration. The map in 2017 added the Dipole Repeller. The map of the future, the one being drawn right now by surveys still ongoing, by telescopes still operating, by analyses still being refined, will add features we cannot quite see yet. What I find genuinely moving about all of this is not the size of the structures, although the structures are large. It is the patience of the inquiry. Generations of astronomers have given their working lives to a picture that none of them individually could have completed. Sandra Faber's work in the 1970s on elliptical galaxies fed into the Seven Samurais distance measurements in the 1980s, which fed into the radio and infrared surveys of the 1990s, which fed into the cosmic flows analyses of the 2000s and 2010s, which fed into the dark flow debates and the Laniakea boundary and the Hubble tension and the next generation of survey telescopes that will, in turn, refine the picture for the people who come after us. That is what science is: a long, intergenerational handoff, a slow accumulation of evidence, a patient refusal to stop asking. The Great Attractor is one of the things that has been quietly answered, in part, by that long handoff. The Shapley concentration, the Dipole Repeller, Laniakea. None of these were obvious. None of them were sitting in plain view. All of them required someone, at some point, to take a careful measurement, write down a number, share it with colleagues, and let it become part of the slow building of a picture that nobody could have built alone. You and I, sitting here this evening, are the inheritors of that picture. We are also, in some sense, walking through the ongoing draft of it. The picture is not finished. Future evenings, future people will know more than we do about exactly what is at the bottom of the basin we are inside of. They will have data we do not have. They will have analyses we have not yet done. They may know things when they sit and listen to the slow voice of the cosmos that we cannot yet hear. That is fine. That is, in fact, beautiful. It is the way the story is supposed to go. We are not at the end of cosmology. We are at the middle. The next chapter is being written by people who have not yet finished writing it. What we have, sitting here this evening, is what we have. It is a map of a flow. We are inside the flow. The flow has a direction. The direction has a name. The name is partial. The picture is partial. The motion, however, is real, and the motion does not depend on whether we have finished naming the destination. The motion is just what we are. Closing reflection. If you have stayed with this story to the end, thank you. Take a slow breath. Let your shoulders soften. Let the room around you be quiet for a moment. Tonight, you have walked through a discovery that took the better part of a century to assemble. You have learned that the stillness around you is the stillness of the inside of a moving universe. You have learned that the Earth is moving with the Sun, that the Sun is moving with the Milky Way, that the Milky Way is moving with the local group, that the local group is moving with Laniakea, that Laniakea is moving toward the Centaurus and Norma direction, and that the deeper destination of that flow is the Shapley concentration, 650 million light-years from where you are right now. You have learned that the flow is partly driven by the gravitational pull of distant mass concentrations, and partly driven by the relative emptiness of the cosmos in the opposite direction, where the dipole repeller, in its quiet way, contributes by simply not pulling as hard. You have learned that astronomers, over decades of careful work, have mapped these features by reading the velocities of galaxies and by listening to the dipole in the oldest light in the universe, and by patching together infrared and radio surveys to see through the dust of our own galactic plane. You have learned, perhaps most importantly, that this entire architecture is not a static thing. It is a process. The cosmos is in the act of becoming more clumpy, of sorting matter slowly, gently, over billions of years into ever more concentrated structures. The Great Attractor is one of the local features of that process. We are inside it. Nothing in the room around you has changed, because you now know this. Your body is still here. Your breath is still moving in and out. The light from your lamp is still falling on the surfaces of your room in the same way it was an hour ago. What has changed is perhaps only this. You now know that the floor under your chair, the planet under your floor, the star at the center of your sky, and the galaxy that holds your star are all in motion together. You are riding a current that is older than continents. The current is moving at 600 kilometers per second. The current has been moving in this direction since long before any animal had eyes capable of looking up. You are inside the flow. You have always been inside the flow. The flow is patient. The flow is slow. The flow is part of what makes the cosmos the kind of place where stars can form, where galaxies can sort themselves into structures, where life, at least in this one corner, has had the chance to emerge and look around. The destination, for what it is worth, is not in any human sense reachable. We are not going to arrive at the Shapley concentration. The Earth is not going to arrive at the Shapley concentration. The Milky Way is not going to arrive at the Shapley concentration. The expansion of the universe will, in the long run, carry the Milky Way and the Shapley concentration apart, not together, despite the gravitational tendency of the flow. That is fine. That is actually part of what makes this story restful when you let it be. We are pointed towards something we will never reach. The motion is real. The pointing is real. The destination is, in the fullness of cosmic time, gently slipping away. We are inside a longing that is older than any species, and the longing does not, strictly speaking, need to be fulfilled. The longing itself is the cosmos. The motion is what holds everything together. The flow is the architecture. If you have ever felt, in the small hours of the night, that you were drifting somewhere you could not quite name, you can now know that this feeling is, in a literal sense, true. You are drifting somewhere, toward the Centaurus direction, towards something we have, in our limited human language, named the Great Attractor and the Shapley concentration. You will not arrive, Nobody arrives. The arrival is not the point. The motion is the point. The fact that we are part of the cosmos, riding inside it, drifting with it, slowly, patiently, toward a destination that has been waiting for us for 14 billion years and will continue to wait for as long as gravity has anything to say about anything. That is the point. Sleep if you are sleeping. Rest if you are resting. The river is still flowing. It will continue to flow. There is nothing for you to do about it. There is nothing that needs to be done. The motion has been going on without you for almost the entire history of the universe, and it will continue without you for the entire future of the universe. You are a brief passenger. You are a careful observer. You are, in some sense, the universe's way of noticing that it has been moving the entire time. That is enough. That is, when you sit with it, possibly the most beautiful thing about being here. The cosmos is in motion. We are in the cosmos. We are in the motion. We are riding the slow, quiet, patient pull of something we cannot fully see, in a direction we cannot fully reach, on a journey that began before our species existed and that will continue long after our last word has been spoken. The Great Attractor, in this sense, is not a faraway object. It is the direction the river is running. We are the river. We have always been the river. We will keep flowing in this same direction for as long as the cosmos has anywhere left to flow toward. Good night. The current is patient. It will still be here when you wake up.